Hello everyone, my name is Chris Emproto. I'm a student at Miami University in Oxford, Ohio, under the advisement of John Rakovan. Today I'll be talking about some of the research I've been doing in fulfillment of my master's thesis on carbonate-hosted apatite in the Grenville Province. The purest and most spectacular deposits of apatite in the Grenville Province occur in poorly understood rocks known as vein dikes. The Grenville Province preserves materials from the largest known collision to have occurred in Earth history from around 1.3 to 1 billion years ago, associated with the assembly of the supercontinent of Rodinia. Grenville-aged rocks are present from Newfoundland all the way down into central Mexico, but there are fantastic exposures in the Adirondack Mountains in New York, as well as in southern Ontario and Quebec. These rocks have relinquished not only many important mineral resources such as precious metals, but also fantastic mineral specimens which grace cabinets and mineral collections the world over. In the field, vein dikes occur as narrow bodies of carbonate rock with coarsely crystallized silicate margins. The term vein dike is a relic from a time where it was uncertain whether these were igneous or metamorphic features. It turns out that they're both in a way. So the current model suggests that vein dikes form during the quelling of regional metamorphism from the partial melting of crustal carbonate rocks. The inclusion of quenched calcite globules in apatite and other minerals in vein dikes is fantastic evidence of their igneous origin, whereas isotopic data gathered by Martin and others is great evidence that these rocks are actually crustal melts instead of mantle-derived carbonatites such as the Magnet Cove complex. So the current model of vein dike formation goes something like this. During continental-continental collision, crustal materials are compressed and heated. Then, during orogenic collapse, there is extension and decompression. Decompression melting of lower crustal materials produces magma and fluids, which go on to cause flux melting of crustal carbonate rocks. These carbonate melts are very low viscosity and are readily emplaced through zones of weakness into shallower levels of the crust, where they may interact with silicate rocks, accumulating aluminum and silicon from their interactions with silicate rocks, and eventually arriving at a silico-carbonatitic composition. The digestion of the host rock results in a coarsening of silicate minerals along the margin, the mineralogy of which is influenced by the host rock. The interactions actually go far beyond the margins, as metasomatic fluids work their way into the host rock, recrystallize it, and destroy the gneissic fabric. Many of the minerals that are common in vein dikes are also common in skarns, such as calcite and apatite, which form the core of these crustal carbonatites. This is no accident, as vein dikes form from the interaction of a carbonate magma with a silicate rock, whereas skarns form from the interaction of a carbonate rock with silica-bearing fluids, so you're mixing the same ingredients at roughly similar conditions. The low viscosity of the carbonate melt means that the advection or flow of chemical constituents can occur with ease, and you can grow massive crystals, such as these basketball-sized nephelines from the Davis Hill locality. Davis Hill is an excellent example of the host rock influencing the mineralogy of the vein dike walls, as the vein dike at Davis Hill intrudes a nepheline syenite, and no other vein dike locality includes nepheline as a major phase in the vein dike. So why study vein dikes? We don't really know much about them, and industrial interest waned around 50 years before the introduction of the theory of plate tectonics. And we know that vein dikes have a very, very important tectonic context. But by studying them, we can learn a little bit more about crustal phosphorus cycling, skarn formation, carbonatite emplacement, as well as the timing and chemistry of orogenic magmatism, particularly volatiles, which are ephemeral and difficult to study. Here's a plot of vein dike localities on a geologic map including the major terrains. As you can see, basically all of them fall within the tan area, which represents the central metasedimentary belt, except for a few that are located in the Adirondack Highlands, which is in the bottom right corner. If you use your imagination, you can see that they fall into somewhat linear trends. I've gone and circled each of these trends. I've divided the Adirondack lowlands from the Adirondack highlands based on geochronologic work in Chiaranzelli et al. 2019, which shows two distinct age groups based on which side of the Carthage-Colton shear zone they fall. I've gone ahead and named each of these trends based on the terrain in which most of the localities are located. They are the Bancroft trend, Frontenac trend, Lowlands trend, and Highlands trend. we learned so far? We see four major geographic trends, the Bancroft, Frontenac, Lowlands, and Highlands trends, and we see almost nothing in the center of the central metasedimentary belt, in the Elsevier and Mazenot terrains. So very few of these deposits have been dated, but the few ages that we do have suggest that they form after peak metamorphic conditions. So, can we look at the nearby materials and accurately estimate an age for vein dike deposits, and if we can, what do these represent? So we're going to guess that the Bancroft trend dates to around 1050 MA, and the Frontenac trend dates to around 1150 MA. If we put an overlay of this geochronologic map from Plume et al. 1994, which looked at ages of minerals that represent both crystallization ages and peak metamorphic conditions, we can try to see the ones that fall near our trends and use those to estimate the ages of our vein dike localities that occur nearby. Highlighted in yellow are localities which have been dated, so we're going to use these to test our hypothesis. Over here in the Bancroft area, we have the Madawaska mine, and in the same trend, we have the Yates mine. Over here, we see ages around 1067, 1060, 1048, 1041, getting a little bit younger, but still around 1050. Over here in the center, in the Frontenac terrain, we see slightly older ages, around 1125, 1121, 1145, so the Parker mine, which is also in the Frontenac trend, is likely of a similar age. Down here in New York, we're going to use the Powers Farm locality to test our hypothesis. Powers Farm is on the Adirondack lowland side of the Carthage-Colton shear zone, where ages are around 1150, 1156, 1137. So let's see how we did. We guessed that the Bancroft trend dated to around 1050 MA. The Madawaska mine, which is in the Bancroft trend, dates to around 1054 MA. That's right on target. The Yates mine, which is also in the Bancroft trend, albeit a little bit further out, is quite a bit younger, at around 1 billion years in age. However, this still fits into our story. So around this time, the Ottoman orogenic phase was subsiding, which progressed into the Rigolette stage at around 1 billion years ago, wherein metamorphism progressed to the margins of the central metasedimentary belt under lower metamorphic grade. So the Yates mine age does in fact fit into our story. We guess that the Frontenac trend was around 1150 MA in age. The Parker mine, which is in the Frontenac trend, dates to around 1140 MA. That's extremely close, and definitely within the margin of error. Powers Farm, which is in the Adirondack lowlands and the same general package of rocks as the Frontenac trend, dates to around 1150 to 1160 MA. That is also consistent with the Parker mine age and our guess for the age of the Frontenac trend. So it looks like our guesses do hold up, and we can look at the ages of nearby deposits to guess the unknowns. So, what was going on during the Grenville Province at this time? Well, at 1150 MA, we have the collapse of the Shawinigan orogenic phase, as well as the asthenospheric upwelling and the intrusion of the anorthosite, mangerite, charnockite granite suite within the Adirondack Mountains, as well as in the Frontenac terrain. At around 1050 MA, we have the collapse of the Ottoman orogenic stage, as well as asthenospheric upwelling and synorogenic intrusion within the Adirondack Highlands and along the Bancroft shear zone. So this is exactly the proper time and place that we see our vein dikes. We should all at least be vaguely familiar with apatite. It's the most common phosphate group mineral on Earth. It makes up our bones and teeth. Many of us have apatite in our collections, but it's also a very important phosphorus, rare earth element, and halogen sink in many geologic systems. We're going to take a little bit of a closer look at the area in the dotted yellow box. So this is the structure of apatite, but in the dotted yellow box, I have cut out the anion column, which is actually where the halogens, fluorine, hydroxyl, and chlorine will sit when they substitute into the apatite structure. So use single crystal X-ray diffraction to indirectly model the halogen composition by modeling the site occupancy where each of the halogens sit and seeing how well that matched the expected site occupancy. So as you can see, there's a mess down around 50 to 65% fluorine, but this is actually a very, very tight compositional range for a geologic system, considering that we sampled 50 localities, all of which had very different mineralogy. There are also a few outliers, such as the nearly end-member chlorapatites from the Bob's Lake chlorapatite locality, as well as a hydroxyl apatite in the Bancroft Trend that just resembled nothing around it. So we're going to combine this data with what we just learned and see if we can pull anything else out of interest. In the Bancroft Trend, we have very hydroxyl-rich fluorapatite, as well as a cluster at around 55% fluorine, 45% hydroxyl. Chlorine is also essentially entirely absent, but there are a couple of localities that have chlorine. In the Frontenac Trend, we see that chlorine is in fact very common, up to around 7% occupancy, although there is the outlier end-member chlorapatite from the Bob's Lake chlorapatite occurrence. We also see that there is nearly an absence of more hydroxyl-rich compositions. Most of the apatite from the Frontenac Trend is more fluorine-rich. There are no 50-50 compositions. And again, minor chlorine is very, very common. Moving on to the Lowlands Trend, we see fairly similar apatite chemistry. So chlorine is not uncommon, but the most chlorine-rich apatites come from the Kelly Farm, which is the locality that definitely most resembles the classic Canadian vein dike occurrences. We also see, again, an absence of 50-50 compositions and a much more fluorine-rich average composition than in the Bancroft Trend. So we were only able to sample two localities in the Highlands Trend, Rose Road and the Owen Prospect. Both of those were very hydroxyl-rich fluorapatite. The Rose Road locality was very, very nearly a 50-50 fluorine hydroxyl composition. So let's plot everything using what we learned from earlier and see if anything interesting pops out. So if you recall from earlier, we learned that the Bancroft and the Highlands Trends are related in age. Let's also see if their apatite chemistry is consistent. So both the Bancroft and Highlands Trends have very hydroxyl-rich fluorapatite, clustering at around 55-45 fluorine hydroxyl, and chlorine is basically absent in these compositions. So even though we only have two data points from the Highlands Trend, they do match up with the extensively sampled Bancroft Trend. Now to the Frontenac and Lowlands Trends, which are also related in age, and so the Bancroft and Highlands Trends were around 1050 MA during the late Ottawan to Rigolette stage, and the Frontenac and Lowlands Trends were around 1150 MA during the late Shawinigan stage. We see that apatite from Frontenac and Lowlands localities is much more likely to contain chlorine to around 10%, although again there is the end-member chlorapatite from Bob's Lake. But we also see much more fluorine-rich compositions and an absence of 50-50 and even 55-45 fluorine hydroxyl compositions. So we can see that the Frontenac and the Lowlands Trends overlap entirely, which suggests that there is a similar source of fluids for the Frontenac and the Lowlands Trends, which is distinct than the fluid source from the Bancroft and the Highlands Trends. So it's possible that they were tapping different sources in the asthenosphere, or perhaps different crustal reservoirs were melting to form the decompression melts, which released fluids, which flux melted the crustal carbonate materials. Let's recap what we learned thus far. There are four major geographic and geochronologic trends: the Bancroft, Frontenac, Lowlands, and Highlands. The Bancroft and Highlands Trends are related in age, dating to the late Ottawan to Rigolette stages at around 1050 to 1000 MA, whereas the Frontenac and Lowlands Trends are related to the collapse of the Shawinigan origin at around 1150 MA. Most vein dike apatite is hydroxyl-rich fluorapatite, and apatite from the Bancroft and the Highlands Trends are more hydroxyl-rich than apatite from the Frontenac and Lowlands Trends. The apatite from the Frontenac and Lowlands Trends also commonly contains minor chlorine to around 7% site occupancy. Chlorine is essentially absent in apatite from the Bancroft and Highlands Trends. So the major conclusion is that we have two groups of vein dike localities which are distinct in the timing of their emplacement as well as their chemistry. So next time you pick up an apatite from the Grenville Province, Think about where it fits into the story of mountains rising and falling, shallow seas closing, and continents drifting together and then apart. Thank you for listening. I'd also like to take this opportunity to thank everybody who contributed specimens to our study. This would not have been possible without the extreme generosity of many collectors and museum staff. Thank you.